everyone. I'm making this video to show a few worked out examples of interval estimates using Excel and the formulas that we're working with. So this first example, we'll just start reading it through. So it says that a study of 420,095 Danish cell phone users, so that number there, this is describing the sample. So the size of the sample here, this would be our N, 420,000. And these are cell phone users, and they found that 0.0321% of them developed cancer of the brain or nervous system. So this is a percentage, or really a proportion, of that sample that have this cancer versus do not have this type of cancer. So I'm going to write this as our sample proportion, and the symbol for that is p hat. But because this is written as a percentage, I need to convert it to a decimal for our calculation. So I'm moving the decimal place 2 places to the left, which gives me an extra 2 zeros there. So really tiny proportion in this case, just because, not very many people get cancer of the brain or nervous system. So based on that, we're supposed to find a 90% confidence interval estimate. So here is my confidence level for the percentage of cell phone users who develop cancer. So this is telling me what I'm trying to estimate. So this is an estimate for a proportion, and this is the first thing you need to determine on these questions is what are you trying to estimate. So this is an estimate of the population proportion. You're going to get some kind of interval. Our population proportion is between something and something, right? So we would expect that interval to be somewhere around the sample proportion, but we're going to compute out what that interval estimate for our population proportion is. And just a little side note here, proportions are always decimals or fractions, but we can also write them as percentages. So when we get the answer at the end here, we will kind of convert it back to a percentage, but all of the calculations with our formulas will be using the decimal values. So since we're dealing with a population proportion, I'm going to check the conditions or the requirements for this. And what I'm looking at for this is on page 328 in the book. This goes through kind of some details about our proportion estimates, including the notation like the p hat and the n, but there are 3 requirements listed. One is that the sample needs to be a simple random sample. Now you'll notice that the homework questions often don't really give us enough information for this. We don't actually know where this sample came from, so I don't know if it's a random sample or not, but this is an assumption that we would have to make in order for these results to be valid. So just something to be aware of. The second condition is that we're meeting the conditions of a binomial distribution, meaning that there is sort of a fixed number of trials where there are 2 possible outcomes where we normally say success and failure, and that those results are independent. So here the trials would be all 420,095 cell phone users, and the success failure condition is whether or not they got cancer or did not. So this is sort of a yes or no answer for each person within the population. And so we are assuming that those results are independent. So if these people were really randomly sampled, they should be, those results should be independent. And the last is that there are at least 5 successes and at least 5 failures. And that sounds a little weird in this context, but basically that means that within this sample, there were at least 5 people who did get cancer and at least 5 people who did not. In this case, the vast majority of this sample did not have cancer, so that's definitely more than 5. You would want to check to see what that 0.0321% of this n value is. We could compute that off on the side. So if I take that tiny percentage of the 420,095, we get about 135. So even though it's a really tiny percentage, there were more than 5 people in this sample that did get cancer. And really, you just don't want either the success or failure categories to be too small. Otherwise, it's just not enough to make conclusions based on. So checking the requirements is kind of just an aside, but we should do that before continuing with the procedure. Now, I haven't said anything about kind of the second half of this question. The rest of this is just looking at the rate of cancer in the population of people who do not use cell phones. And we're going to kind of compare our answers that we get to that. So the second part is sort of a second question after we're done with the interval estimate. So I'm going to set that aside for now. The next step in my process is I need to find the critical values. Now, because this is an estimate for a proportion, that means that we're going to be using the normal distribution. So these are going to be z values. My critical value is going to be z alpha over 2. And I've already done a video about finding the critical value, so I'm not going to go into a ton of detail here, but I'm imagining cutting off the two ends of my normal distribution. Because this is a 90% confidence interval, I'm going to have 0.9 as the area in the center. The alpha value here would be 0.1 or 10%, and the area in each tail would be half of that, or 0.05. So I'm going to take that information over to Excel and use that to find my critical values. So I'm using the norm.inv function. The area to the left of my left critical value is 0.05. Then I'm using 0 as the mean and 1 as the standard deviation, since this is a standard normal curve. This is the negative value. This is the one on the left. The positive one would just be the same number, but with the opposite sign. So 1.64485, this is really what I'm going to be using for my critical value in the calculation. Okay, so there's my critical value. Once you have the critical value, you can go through to the formula for computing the interval estimate, and I've got that pasted in my notes here. So this is an interval, again, estimating the p-value, the population proportion, and this is going to be computed by taking p hat, or the proportion in the sample, and both adding and subtracting our margin of error. So the first step here is to figure out what is the margin of error. This is z alpha over 2. Z alpha over 2 is that critical value that I just computed. So this is the number from Excel from before. And then I'm going to have the square root of p hat times q hat. So p hat we already wrote down. There's my p hat, the sample proportion from the problem. Q hat, this is just like the p and the q from the binomial. Q hat is going to be 1 minus p hat. So 1 minus 0.000321. Notice that I'm using the decimal values there and not the percentages. Otherwise, this won't work out the same. And then our n value, this was the size of our sample, goes in the bottom. So we've got this big square root here. Now, you can definitely do this on a calculator if you want. Just make sure you're using order of operations. So start with the 1 minus, or the q hat piece, multiply by the p hat, divide that by n, then take your square root, then multiply by the critical number. So kind of working your way inside out. But I tend to do these in Excel, and so that I can just do this as one big calculation. I'll show you what that looks like here. So I'm going to do, so this is my margin of error. E. This is the critical value, which I already computed. I'm just going to click on that cell, times. I need the square root, which is SQRT. My p-value, I'm going to add some parentheses here for the numerator, so extra parentheses, type in my p-value times the q, which is 1 minus that same number, close my parentheses for the top of the fraction, then divide that by 420,095, close the parentheses for my square root, and there's my formula. Bam. So this is my E value, my margin of error. This is a really tiny number in this particular problem, but I'm going to take that value and I'm going to add and subtract it to the sample proportion. So this is p hat minus E and p hat plus E. So I'm going to take my p hat, which was 0.000321, and subtract this margin of error value I just computed, and then do the same thing with plus. And so this gives me two values here. Let me write them down. So this tells me that P, my population proportion, is somewhere between 0.0002755539. Probably don't need all those decimals, but 0.000366461. So this is giving my lower and my upper bounds for P. Now these are the proportions as decimals. I could also rewrite these as percentages, which would probably make sense in this case. So this is between 0.0276%. I'm just going to round to the same number of decimals as the original p hat was, up to 0.0366%. So based on this sample, I think that the proportion of all cell phone users in the population is somewhere between about 0.027% and about 0.036%. Now, this particular problem wanted me to do more than just find the interval estimate, but it also had this question. So prior to this study of cell phone use, the rate of such cancer was determined to be 0.0340% for those that are not using cell phones. Based on this, do cell phone users appear to have a different rate of cancer from non-users? So I'm comparing this rate for non-cell phone users to the rate that we came up with for cell phone users. And what you see is that for non-cell phone users, this percentage falls in this interval. So it doesn't seem like the proportions for cell phone users and non-cell phone users are any different. There doesn't seem to be evidence for that, at least from this sample. Okay, example number 2. Here we're looking at a small sample. These are mercury levels for tuna from different stores in New York City. So it's a very small sample. There's only, let's see, 1, 2, 3, 4, 5, 6, 7 items here, or 7 pieces of tuna that they checked. And looking at these, the FDA says that mercury level should be below 1 part per million. These values here are in parts per million. So based on this sample, we're supposed to construct a 98% confidence interval for the mean amount of mercury in tuna in New York City. So again, first question, what are we trying to estimate? Here, this is going to be an estimate for the mean of the population. So my goal is to come up with a range or an interval of values from an estimate for how much mercury is in tuna in New York City. We've got the sample here. I need to actually take these values and put them into Excel, because what we're going to need to compute will require the mean and the standard deviation of this sample. So let me actually get our formula first so we know where we're headed. All right, so here is the formula for a mean. You'll see that the calculation is actually very similar to what we saw for proportions. We've got an x bar plus e and an x bar minus e. E is again the margin of error. You'll see that the calculation for this is a little bit different than what we saw for proportions, but kind of similar. And then the x bar, of course, would be the sample mean rather than the p hat, which was the sample proportion. But otherwise, they're pretty similar. So we're going to have to find the critical value. This is a mean estimate where we do not know sigma. We don't know the population standard deviation, and that is typical. So this is going to be a t value. This is coming from the student t distribution. And again, I'm imagining my little picture, chopping off the two tails. This is a 98% confidence interval, which means I have 0.98 as the area in the middle. The alpha here would be 0.02 or like a 2%. And that means that each tail would have area of 1% or 0.01. So I'm going to come over to Excel so I can compute my critical value. The critical value, I'm using the t.inv.2t function. So this is the two-tailed one. And because it's using two tails, I'm actually just going to put in my alpha value rather than the area in a single tail. This is the area in both tails together. And I also need the degrees of freedom. Degrees of freedom for these problems is n minus 1. So n in this case is 7. So this is going to be 6. And here is my critical value. So I'm going to need that for my calculation, and what I'm going to do is I'm going to take that critical value, put it in for my E, so that 3.14 number, that's my T alpha over 2. Then I need S divided by root N. Now N is 7, but S is the sample standard deviation. I'm not given that in the problem, but I am actually given the sample. So I need to take these numbers and put them into Excel. My 7 numbers, I'm going to go ahead and compute the standard deviation of my sample. This is S. And I'm going to go ahead and find the mean as well. This would be my x bar, because I know I'm going to need that in the next calculation. Okay, so I've got my S value. I'm going to put that into the formula, and I'm just going to, again, compute this using Excel. So this is going to be my critical value. I'm saying that times S, which I just computed here, and that is divided by the square root of n, where n in this case was 7. Okay, so there's my E value, definitely a lot bigger than the last one we looked at. And so my mean interval estimate is going to be the sample mean, x bar minus E, and then x bar plus E to get the lower and upper bounds. So I'm going to compute that here. My x bar, my mean of the sample was 0.71857. So I'm going to take that, I'm going to do subtracting my error, my margin of error, and then do the same thing with a plus. And just like with the proportions, you can definitely just do this with a calculator. There's no need to use Excel except for finding the critical value itself. But I just find it easier to do this. So what this tells me is that my mean is going to be between 0.284 and 1.153. And these would be in parts per million. So this is actually a pretty big range considering the size of these numbers, and that's really just because this is a very small sample size, so you can't really get a confident estimate with this small of a sample size without it being a pretty big range. But based on this, this would be cause for concern, because this means that the mean amount of mercury in tuna does seem to be higher than the prescribed 1 part per million, or at least it might be. So this would be something that says, yeah, maybe we should take a bigger sample and see what's going on here. All right, last example here. This is going to be an interval estimate for a standard deviation. This is the third type that we're looking at in Chapter 7. So here this says a clinical trial was conducted to test a drug for treating insomnia. After treatment, the 16 subjects had a mean wake time of 98.9 minutes with standard deviation 42.3 minutes. So I want to try and make note of these things. So this is information about the sample. This is telling me we've got 16 subjects. So this is my N. That's the size of the sample. The mean amount of wake time they had, this would be X bar. That's how long they were awake on average. And the standard deviation, again, standard deviation of the sample, of that sample wake time, was 42.3 minutes, which is quite a large standard deviation if you look at that compared to the mean wake time. So people were awake for a little over an hour and a half, but with a pretty big range of values there. So assuming that the sleep values come from a normally distributed population, construct a 98% confidence interval estimate of the standard deviation. I just realized that I did not include a check of the requirements on the previous problem that we did. Let me just make a note of that here. Requirements. The requirements for a mean estimate are on page 342 in our book. There are two requirements. One is that the sample is a simple random sample, and the other is that either the population is normally distributed or N is greater than 30. So the first is pretty common. We need a random sample. Again, in this problem, I don't actually know whether this was a random sample or not. If it was not, then none of our predictions here really mean anything, because if it's not a random sample, we can't really say anything about the population. And the other requirement actually may not be true either in this case, because our sample is not bigger than 30. The N is only 7 here. And I just don't know whether the amount of mercury in fish is normally distributed or not. So underneath requirements here, maybe we should put some big question marks. It's not clear whether we've met the requirements in this particular example. If not, then we just can't find an interval estimate though. Okay, so back to our standard deviation problem. So again, what we're trying to do is do an interval estimate for standard deviation of the population. The requirements, you'll see these on page 362. There are two requirements. One, the sample is a simple random sample, which again, it doesn't really say here, so we have to kind of assume that these 16 people were selected randomly. And then two, the population must have normally distributed values even if the sample is large. So this is a little bit different than doing a mean estimate in that that requirement of normality is very important, even if you have a big sample. So it is kind of important that they are telling us that this is coming from a normally distributed population. So that means that the amount of time people are awake at night is normally distributed in general. Okay, so based on these, I'm going to go ahead and find the critical values. And if you want more details on finding the critical values, take a look at my video on that. This is a 98% confidence level, so that would be 0.98 area in the middle, and that means 1% or 0.01 area in each end. This picture here is not really representative of the chi-squared distribution. It looks a little bit more like the normal curve, but I'm expecting my left critical value and my right critical value to be situated something like this. So the area in each tail is 0.01, the area in the center is 0.98. So I'm going to switch over to Excel so we can find those values. Okay, so for my left value, I'm going to use the chi-square.inv function. So this is the left value. That probability value that I'm typing in here needs to be the area to the left of the critical value, which in our case is 0.01. And the degrees of freedom is, again, 1 less than n, or 1 less than the sample size. This sample had 16 people in it, so this is going to be 15. And then I'm going to do the same type of thing for the right side, chi-squared.inv or chi-squared.inverse, but I'm going to use the right-tailed version so that this 0.01 here can be the area to the right. My degrees of freedom is still the same. All right, so we've got our left value and our right value. These are going to go into the formula for our interval estimate for the standard deviation. Here is that. So this is the most complicated looking formula of all of them. You'll notice that it looks quite a bit different from the other two. There's not an e that we're adding and subtracting. So we have to compute the upper bound and the lower bound separately. But these two sides of the inequality, the upper bound and the lower bound, are very similar. They both have a square root on the outside. They both have an n-1, so in our case that's going to be 15 in both cases. And then s squared, so that's our standard deviation squared, 42.3 on both cases. And then in the denominator, we're putting these critical values, the left and the right. Now notice that the lower bound has the right critical value. That is the larger of the two. In this particular case, that was this 30.57791 value. And the left one is in the upper bound. That's the smaller of the two numbers, 5.229349. So pay attention to those left and rights. If you flip around, of course, your interval is going to be backwards. The other common mistake here is that we are not actually squaring these numbers. These are from the chi-square distribution, so they're sort of already squared. So this is exactly what we would want to compute for those lower and upper bounds. You can definitely do that on a calculator if you want, or we can do this in Excel. This would be square root of 15 times our standard deviation squared divided by the right critical value, and then square root of 15 times standard deviation squared divided by the left critical value. So this is telling me that my sigma, my population standard deviation, is somewhere between 29.6 and 71.6 minutes. So this is giving me an idea of how much these wake times would vary within the population of people taking this drug. And it's a little bit hard to reach conclusion here, but it does seem like this range, this standard deviation is quite high. So unless it's really bringing down wake times for people with insomnia by a lot, it might not, the variability might make this treatment not really worth it. All right, so that's all three examples using the three different formulas for finding confidence intervals. That's everything for this video. Thanks.